Hi, so our paper is titled Evaluating Concurrent Robustness of Language Models Across Diverse Talent Sets. I'm Vatsal Gupta and I have Pranshu Pandya with me. We're both from IIT Guwahati. We've done this paper and this project in collaboration with Tushar Kataria, Vivek Gupta, and Dan Roth.
Language models has continuously becoming integrated in our day-to-day life, and with this the reliability is become very crucial to us. Currently, language models can display unexpected behavior when they see very slight changes to their input. We call these changes perturbation. Now, there has been extensive analysis on single kind of perturbation, and there has been study to make model robust on that. But when the model is trained on a data set and we need it to be robust across multiple perturbations, there isn't any solid framework which explain us to make model robust across multiple perturbations.
We now move to the problem statement. So, from what we have analyzed and from our motivation, we mainly see that the main problem that we have is to propose a multi-set inoculation framework such that the model can be made robust to multiple type of perturbations, and how this framework can be used to analyze the concurrent robustness problem and address that issue. We also start to think about what possible strategies can work and how they compare against each other in different settings, and how we can propose cost effective strategies for both pre trained language models as well as large language models, such that they're generalizable to different kinds of NLP tasks.
So in our methodology, we start with a pre-trained language model and fine-tune it on an original unperturbed dataset. Then we create a perturbed test set with different input perturbations and we call them our challenge set. We apply different inoculation strategies on using this challenge set on our initially fine-tuned model. First of the strategy is sequential training, where we fine-tune the model sequentially one by one on each of the challenge set. Next, we have mixed training, where we combine all the challenge sets and create a combined fine-tuning set, which has all the perturbations randomly distributed across the entire combined set. In both sequential and mixed training, we had same number of same number of examples for each of the perturbations, but we can even have different number of perturbations according to different parameters like and with that we got dynamic mix strategy, where we have different number of examples of different perturbation.
So, akin to these strategies or creating analogs of these strategies for LLMs, we propose a prompting with chain of thought prompting and also giving exemplars and making the model elicit reasoning. We propose perturbation aware prompting, where the model knows that the input that it's getting might possibly be perturbed. And from this, we propose a single exemplar multiple prompt, which is basically a prompt which is tailored for one particular type of perturbation with description and exemplars for that particular perturbation type. We also propose the multi-exemplar single prompt strategy, where we have detailed exemplars and descriptions covering all the perturbation types and making the model elicit reasoning again when it gives out an answer or it gives out a label. Under this, we have MESP MPI and MESP MPE. MPI or instructional focuses more on detailed descriptions, and MPE or exemplar focuses more on exemplars, along with the description and making the model tell what mistake it's identified and what's the correction it is proposed.
Now, using this framework, we will analyze a case study of a tabular NLI. For this, we utilize the very famous tabular NLI dataset InfoTabs, and on that, we created 5 different perturbations. We are also using the original alpha 1, alpha 2, and alpha 3 test sets from the InfoTabs to analyze how much the model's performances on the original test sets. The 5 perturbations that we are using are character, numeric, negation, paraphrasing, and location. And we can see their examples in the image on the left side.
So when we are selecting how many samples or what samples to perform the training on, we select only the pertinent samples post perturbation. This also involves a determinantal point process where if we have too many samples, then we're selecting only the samples which we know are going to be difficult or which the model can learn like a lot about the perturbation from. We present the table in a paragraph fashion. We employ alignment techniques from Yadav et al, and we employ the representation in a paragraph format, which we've adapted from Neera's paper. You can find the citations below. The metric that we use for evaluation is just simple accuracy, which in our case happens to be the same as micro F1 score. So we label the hypothesis as entailment, contradiction, or neutral as the NLI task goes, and then we see what the performance is over the baseline. The baseline being how much the model is performing when it's trained only on the unperturbed set. We analyze performance on both pre-trained language models as well as large language models. In our specific case, the pre-trained language model that we are using is Roberta Large, pre-trained on the InfoTabs dataset. And large language models, the baseline performance is when we just give a normal prompt talking about the NLI task and saying that we need the model to label the hypothesis from the premise.
Moving on to the result, let's first establish the need for the concurrent robustness. Here we can see in the multimodal uniset inoculation format, when we just fine-tune a model on a single type of a perturbation and evaluate it on the different kind of perturbation, we can see that when the model is fine-tuned on a particular perturbation, it performs well on that respective perturbation as compared to the baseline, but its performance deteriorate as compared to the baseline for the other perturbation types. And this suggests the need for a concurrent robustness where model is performing well across multiple perturbations when fine-tuned on these challenge sets.
So, moving on to the results that we obtained from the different strategies for pre-trained language models, we see that Roberta fine-tuned on InfoTabs when put through the mixed or the dynamic mix strategy performs much better than the sequential strategy. We attribute this to the fact that when you train a model on different type of perturbations in a sequence, the samples which it obtains later are remembered much better than the samples which it got earlier. This is called the catastrophic forgetting problem, which is well documented and well analyzed in other papers as well. Moving on to the mixed and the dynamic mix strategy, the mix strategy obviously performs much better than the sequential strategy because of this very reason. But we also see that for the same number of total samples in mixed and dynamic mix, we see the dynamic mix strategy performing much better. For the same number of 1500 samples in dynamic mix, we see an average performance or an improvement of 7.85 points. But on mixed with 300, which is 300 samples each perturbation, total of 1500 samples, we see a 7.02 performance on an average, 7.02 performance points improvement. Um, we also see that as the number of samples increase, we see an increase in performance for both dynamic mix as well as the mix strategy. This is quite obvious because if the model is able to see or is able to gather more samples or more diverse samples of a particular perturbation, then it learns more on that. And because we're regularly providing it with new samples of that perturbation, both mixed and dynamic mix, it is not losing out on the information of one perturbation throughout this process, unlike sequential, where we see a degradation in performance for with some sequences as well.
As we seen that mixed training is the dominant strategy out of all the strategies, and thus we conducted ablation study to analyze how mixed strategy performs across for the unseen perturbations when it is performed on a subset of the perturbation. So here in the two tables we have performed the mixed training of the model for nag num log, and for the second table we have performed it on the character and numerical. We can see that when we fine tune on the character and numeric, the model performs well even on the out of distribution perturbations. And this we can see that mixed training is extendable across unseen perturbations also.
When we start to analyze the results for large language models, CMP is basically an analog of the multi-model uniset inoculation strategy, where we expect that when we tell a model or when the prompt is provided with the information for a particular perturbation type, we expect the performance to be the most on that particular perturbation type, which is more or less true that when you train the model on the character type. By training here, I mean that the prompt is provided with description of what the character perturbation is along with exemplars. Then we see the highest performance being attributed to the character perturbation itself. In this column, we see that the highest value is 67.6, which is when the model has been told that it can expect character perturbations to be in play. Surprisingly, though, when the model is trained on the character perturbation, we see the highest performance even for other perturbations on by training it on the character perturbation itself. But still, we see the general nature of training and then testing on that particular perturbation being true even for LLMs. We see a high performance, we see a high value across the diagonal over here, and Q dash just represents how the performance is on the unperturbed data set. We see the highest value as being 73.76. This is happening when we've trained it upon the paraphrasing type. Basically, when you tell the model that a sentence can be structured in different ways, then it becomes more sensitive to seeing different nature of that particular sentence and then giving out a label. The first table is results on GPT 3.5 and the second are results on Llama 2, the 70 billion version. Moving on to the next MESP strategy.
Here we can see that we are providing multiple examples within a single prompt. So each of the perturbation type gets 2 or 3 different examples where we show how how different perturbation can affect the hypothesis and how models should identify those perturbations. The multi-exemplar single prompt strategy consists of 2 different types of prompts where the MESP MPI and MESP MPE. We can see from the figure that although MESP MPI and MPE are both better than the baseline, the MESP MPE where we provide more examples is dominant as compared to MESP MPI where we provide more instructions. In conclusion, we can see that the concurrent robustness is really a very difficult problem, and we have provided a very comprehensive framework to study the problem, to create a perturbation sets and study it with different strategies. We established that mixed fine-tuning as well as multi-exemplar single prompt strategy for PLM and LLM respectively are the dominant strategies to improve the respective models on the concurrent robustness problem.
Finally, we also think that there are some future directions which we can explore. The complex sample selection is a very obvious thing that we can do additionally. We can adopt more advanced sample selection strategies, which can include dataset cartography to have hard sample selection or we can also propose more complex algorithms for selecting samples for robust training from an unbiased selection of samples. We've given the necessary citations and you can see them below. Also, we would like to analyze the composite perturbation effect, where we extend the concurrent robustness problem to concurrent composite robustness problem, where we can have successive perturbations applied to a single sample. You can have, say, character and then the numeric and then the location perturbation applied all to the single sample. We represent this by pi I of pi j of x, where pi I basically means the application of perturbation type I to a sample x, and then we can see the combined model performance after applying perturbations compositely. Thanks a lot for hearing us out. We would be happy to discuss any further questions that you have, and we'd be really happy to discuss any further questions that you have. And you can please do visit our website and you can go through our paper as well.